So hello everyone, this is problem session 10 of the homotopy type theory track of the HoTTEST School 2022. We'll, as usual, be working through the worksheet, dealing with this new concept of propositional truncation, the way it was introduced in the lecture. So if you come from the Hod book or Egbert's book, where they introduce the general function for K truncation, we'll be trying not to use the same notation, and we'll be just trying to use solely the concepts and the notation that was available to us in the lecture, just to make sure that if you're not following the book, you'll still be able to understand. However, I will be making a reference to a proposition or two, I think, in Egbert's book. One thing that I wanted to mention beforehand is that it's quite a lengthy worksheet. So if you're here on YouTube and watching this as a recording, and you want to hear about question number 6, I urge you to check the other problem session that will be recorded in the American time, and we'll probably cover problem 6 instead. What we'll be trying to cover is everything up to problem 5, just to make sure this is a reasonably timed session and a reasonably timed video. Okay, so with that said, as usual, if you have any questions, please feel free to ask them. And cooperation is always fun and good, and much better than just sort of going through the notation and solutions. Okay, so let's start with problem 1, which basically just is a really nice introduction about how to handle our proposition concepts, trying to make sure that we're comfortable with actually using sort of inducting and how to construct functions out of propositionally truncated types. So let A be a type. Problem A says that we have a biconditional going on with doubly truncated A and singularly truncated A. Okay, so to show this, we need just pair up 2 pairs of implications. So in the forward direction, want to show that we have function of this type. And here I'll be sort of going very slowly just to make sure we sort of unravel everything that we need to have. Egbert has said that one of the things that he wants his lectures to sort of give you are soft skills and how to present these sort of type theoretic proofs. And so I'll be trying to maybe facilitate that by going slowly through all of it. So okay, we want to show this. Note, by our assumption, A is a proposition. So by the equivalence, what equivalence do we have when we have a propositional truncation? We have an equivalence of functions from this truncated type and the functions from its untruncated version, I should say. So suffices to get this function, which is just identity at the truncated A. So we get this direction quite easily. The other direction is even nicer. So remember, we have this unit of truncation of A from A to its truncation. This is our truncation map. So we also have something that we've defined in class is the truncated map from A to the double truncation. Or alternatively, just also the unit of the truncation itself. Okay. So both of these will suffice. And with that, we're done with part A. So that was sort of quite nice. So let's go with B. So we need to show that there's also this biconditional. It's an A, truncated version of B of X. Okay, but here B is of course a type family over A. So I'm not introducing it formally, but assume everything type checks. We need this function here to the truncation of this entire statement. Okay. So what's this? This by definition is, oh, I have a question in the chat. That exists not the same as sigma more. Yeah. So that's it's very important now to understand that we're trying to think of propositions as actual propositions. So existence claims do not give you actual witnesses. So it's very important to remember that, and it's a very good way of thinking about the fact that actually it's something that I think Jakobson's book has, that there's this motto that every logic is a logic over a type theory. So you can think about this way of saying that, well, we actually are very careful with defining this exists. We're not just using the Kawakari interpretation as basically saying that, you know, logic is just a truncated way of doing type theory. So it's a very good motto, I think. I think that's just what's it called? Just like categorical logic, I think. No, I don't remember currently. Yeah. Oh, yeah. Jacob. Okay. People with surnames starting with a J. But yeah, so there's this motto there, I think, in the beginning of the book, and I think it's a very good one. Okay, so let's go forward with recalling what the definition of this is. So it's just this truncated version of X and A, Bx. And so suffices, show this biconditional here. Okay, so in the forward direction, truncations, I should say, I'll be using -1 truncated and propositionally truncated similarly for sort of evident reasons. So -1 truncated, truncated types are props. So we can use the equivalence to instead construct type. So basically, we're just assuming that we actually have an element here. And now we have X and A Bx. Okay. Categorical entry to type theory, right? Oh yeah, very pre-hot. This was this was a time where, well, we haven't figured too much stuff out still, but that was very early on, sort of trying to introduce very nice semantics of dependent type theories. Okay, so we need to send some x in A and y in the truncated version of B of x somewhere. The question is where? Define a function from bx to truncated version of the sigma type. Again, by using the equivalence, with actually assuming we have a term of time bx, since again, the truncated version of the sigma type we're given here is a proposition. Okay, so where will we be sending it? We'll be sending, right. So y so let's say we have here, and f is defined by sending y to, so the unit apply to x and y here. And the unit over truncation is over x and a bx. So is that clear what we did just there? So we have x in the context already. And so we so this is an element of the sigma type, and we have the canonical unit of the truncation, which lets us get into the truncation itself. Okay, good. So let's say define given x and a. So okay, so we have this, and so so our function is what? So we have x and y. Again, this is our original function that we still have unresolved. Sending our x and y to eta of a b x and f of y. I think I wrote something wrong. This is, I mean, what we have above is more than suffices to construct our function. Okay, so this is yeah, this is exactly what we need. Okay, so sorry for the mishap there at the end. Everything good? Everything clear? All right. So in the other direction, what do we need? We need a function from this totally truncated sigma type to this doubly truncated one. Okay. So suffices to get the one from the untruncated version. Okay. But this should be quite okay. So we have our dependent pair x and y here. What do we do? Well, we want to get into this truncation, so we want to apply the unit of our truncation of this large truncated type. Hopefully my handwriting is clear. There are a lot of subscripts here. And so then we have an element of A, and then we take the eta of B of X, the truncation of this fixed type in the type family, and apply it to Y. And this should give us our biconditional. So note, by the way, since we're establishing biconditionals of propositions, this actually gives us some really nice equivalences to work with. Okay. So now we have part C. Okay. Of negation of negation, propositional truncated version, and the negation of A. Okay. So this is sort of a very classical thing that you want to consider intuitionistically. Unfolding, we need a function following form to empty, biconditional with A to empty to empty. Okay, so this is just unfolding what we define negation to be. So in the forward direction, let f be a function in the negation, in the double negation of the truncated type. And let g be a function from A to the empty type, right? So we introduce all the needed parts. So want to find some term in the empty type. So define. So we have this function f. So we want to apply it to something. So we define an element of this function type. Okay, so that we can apply f to it by sort of precomposing unit of g from the equivalence between A empty type and a type untruncated. So the point here being that the empty type is a proposition, so everything works nicely. We can actually use this property. F applied to this function works. Okay, all good. In the other direction, oh, I have a question here. Is truncation a monad? In which sense? Right. I'm not sure whether I can answer from the get-go. That's actually remind me of this question after the session. We'll be able to discuss it. But generally, it's sort of hard to tell from the get-go. There are a lot of things to consider. I haven't considered it, but it's an interesting question. Okay. Okay, so in the other direction, suppose we have a G, the double negation of A, and F going from the truncation to the empty type. What do we need? So need the empty type to apply G2, and we are done. However, again, the empty type is a proposition. So we have our equivalence here. So F goes to some mystery F prime here. So F prime suffices. Okay. Everything nice? Okay. And so our final part, B, is the question of the fact that decidability of A allows us to actually construct a function in the other direction from the truncation of A to A. And so recall what this is. This says that we either get A or negation of A. Okay. So let X be a term of A plus the negation of A. Well, as long as we get some, basically the problem with truncations, as opposed to contractibility, is that you don't actually get a point in the truncation. So, but decidability is sort of either, truncation is about checking whether something is a unit or the empty type. So decidability actually lets you sort of get all the information needed. Either lets you get a point, or the fact that A gets you a contradiction. Okay, so the way we proceed is by induction on X. If X is some element of A, let me write it this way to be explicit, then we simply define a constant function, right, from A to A by mapping X to A. If X is in right of F from A to the empty type, then we know, again, as the empty type is a proposition, and we have the following equivalence. Apply, so assuming X in the propositional truncation, apply the corresponding function to get a term of the empty type, and use induction. And this gets you all that you need. Okay, so this lets us get done with the first problem. So again, this was a little bit cumbersome, I think, other than the last question. Probably, well, the first couple of questions, they are supposed to be giving you a couple of nice equivalences, which are supposed to simplify some logical questions that you maybe want to formalize in HoTT. The last one is probably the most interesting one. However, most of them are just basically making sure that you know how to use propositional truncation. So again, if you see in the solutions, this one truncated, like not one truncated symbols, but like this one bars instead of double bars, which we usually use, those are just the constructors that are used when considering truncations as a higher inductive type. So if you haven't seen them, don't worry. As I mentioned in this session, we're just using the notation that was granted to us by Egbert during the lecture. Okay, but generally you can, it's, you know, it's, those are supposed to be equivalent principles. So, you know, you can always look at the book if you want to make sure you understand the notation there as well. Okay, so any questions thus far? Okay. So now let's look at problem 2. Problem 2. So let A be types, P, Q propositions, and we have a function f from A to P and G from B to Q. The first problem is suppose F and G are propositional truncations. So remember, what this means is that precomposing by them when you have a codomain is any proposition gives you an equivalence. Right, then the product of these from n times b to p times q is a propositional truncation. Okay, so this may be a little bit convoluted, so bear with me. Okay, so we want to consider, so fix a proposition T. Okay, and consider the precomposition map by product from P times Q T to E times B to T. So note by previous problem set, I should say, my previous worksheet, both domain and the co-domain are propositions, since they land in a proposition. Okay, we proved the dependent case actually in the previous worksheet. Okay, so to show an equivalence suffices, well, ek is a very unfortunate shortening of the word equivalence. It can mean many things, so equivalent, to show an equivalence suffices to construct the function in the other direction. It would be to T to P times Q to T. Okay, so that's exactly what we're going to do. So let H be of type, function type of a product A times B to T. Okay, So what do we need? Version of this sort. Okay, so by induction, suppose P and Q are in product. Okay, so need an element. So need an element of T. Okay, so recall that we have this currying going on, A to B to T, and generally with any other types, not just the ones I instantiated here. So in particular, we have that precomposition by our F, which we suppose is a propositional truncation. So we have this equivalence, have this here. So in particular, where this is equivalent to P times Q to T. Okay, so so suffices to get A to QT. Okay, but moreover, we have the equivalence, and again, we can use these equivalences since the function types are actually propositions, so everything works out well, again, by the previous worksheet. Okay, so we have this equivalence as well, which is G from B to T. Right. So given A suffices to find a term of the function type here. So define it by sending B to H, which it's been a while, but we introduced it here, which originally from our product. Okay, H, A, and B. Okay, so again, A is now available, so everything works out. And so by passing through equivalences, we are done. Okay, so I haven't looked exactly at what the solution said, so maybe this is maybe a little bit different from what it's done, but it's essentially the same. What you need to be using are equivalences that you get from these propositional truncations. Okay, and really we didn't even need to introduce these pairs that we had before. Okay, any questions at this point? Let me quickly get a glass of water. So I had a question in the chat. So passing through equivalences, what I mean is by simply, going back. So we said that it suffices to find like a function from here to here, from there to there. So what I mean is simply, we got a function here, so we get a function here, and hence, we get a function here, and so we get a function here. So it's just basically going back through the equivalences we established. What I'm trying to say is, in the usual mathematics, we'll say it suffices to show this, it suffices to show that, right? And type theory, we want to produce an actual term. So the only thing that I mean by that is that you actually apply the equivalences you used, and hence get your previous results. Is that clear? Okay, nice. Yeah, sorry. These jargons keep appearing everywhere. Okay, so now we have part B. So claim for types A and B, we have that truncation, propositional truncation works well with products. So equivalent to A times B. Okay, so for this, just consider a simple diagram. So we have A times B. And what do we have here? We have here we want to have this. Here we want to have this. So these are two propositions that we want to consider. Remember that a product of propositions is a proposition. Here we have the usual unit of truncation. And here we have a product of two individual truncations. So this is a propositional truncation. By previous theorem, so both of these individually are propositional truncations. So their product by previous proposition, this is a propositional truncation. And hence, by a theorem in class, by proposition from class, we get an equivalence happening here. So all is well. Okay. Nice. And with that, we are ready to move on to problem 3. So we already have so many different notions, I guess, of equivalence. So this is another good one to consider, at least logical equivalence here. So consider a map F between types A and B. Claim F is an equivalence if and only if F is surjective and embedding. Okay, so this is a good way of sort of, again, thinking about equivalences that very much sort of piggybacks on a lot of our notions that we use in set theory, right? So we usually identify sets by bijections. Here we have a little bit more structure, so we don't just say that we need something that's surjective and injective. We need an actual embedding. We need a map which actually works well on categorically on the morphisms, on the paths, and so this is actually what's gonna give us this actual result. So F is both surjective and embedding rather than injective, gives us an equivalence. So let us go to the forward direction. So proof. In the forward direction, what do we have? Suppose F is an equivalence. Then we already know that it is an embedding. This is sort of the classical theorem we already showed. Moreover, remember that being an equivalence is the same as having contractible fibers, and this I should say the fact that they are contractible means that the preimage is inhabited at every point, right? So remember is contra fib f b for b in b. We have is defined as right. So exists some a in large A such that for all A prime in A. Well, the point is that just not to overcrowd with notation, but contractibility lets us actually produce a sigma type, which allows us to actually get a witness to what we're contracting at. Okay. And so with this, we're done in this direction. Okay. So give me a second. Maybe I should mention something else. No, I think this all should be good. So in the other direction, have sort of the following happening. So assume right, this place logically equivalence is both. Yeah. So as soon as you have a biconditional of propositions, everything works well. Okay. Can you hear me, by the way? I think my Zoom froze a little bit. Okay. As long as you can see me and hear me, all should be good. Okay. So let's continue. And you can see my screen just fine. Nothing is glitching, right? Okay, so I think that it's just something on my end, so don't worry about it. Okay, so so assume F is surjective plus an embedding. So now need what do we need? We simply can talk about contractibility. So instead, now need a term of, again, by the previous worksheet, we know that instead of equivalences in the usual sense of having these quasi-inverses, we instead can talk about contractibility of fibers. So we now need a term of, for all B and B, have that the fiber is contractible. It's contractible fiber at of F and B. Okay. Right. Did I answer your question, by the way? Yes. So if both of them are propositions, as long as you get a biconditional going on, you automatically have an equivalence. So all good. So the definition of surjective was surjective is for all being B, there merely exists A and A such that we can actually inhabit a fiber. Okay. So that's surjective F that's how it's defined. Okay. So this is actually a proposition, as you can see. Okay. So okay, what do we need afterwards? So here is where we need to use proposition 15.2.3 from Egbert's book. So F is surjective, actually implies that the precomposition function here fiber of F and B to A is contra fiber of F at A is an equivalence, as is contra. And so the entire pi type is a proposition. So the proof is sort of gotten by diagram chasing. You know, it's not that nice in terms of writing this out. There are some things that you will really need to check by yourself. I guess I just wanted to quickly draw the diagram. Let me make sure that I actually have everything here to go over it, right? So the diagram that we want to draw is, so what we basically want to do is factor. And this is not only for is contractible, but the entire, but any proposition you can put instead of is contra. Okay, so here we factor as in the following diagram. Okay, we factor it as pi b in B is contra fiber of F and B. Here we have precomposition. this is the needed type here, f of a. And how do we factor it? Well, first, we sort of, as long as we get that the fibers are merely truncated, we want to get our proposition. So here, get merely the fiber of f and b. Then is contra fiber f and b. Okay, and this map sends h assumes y, and it's just a constant map of h at y. Then afterwards, we go to this type pi in B, we untruncated it. Fiber f at B. And so here, what do? We take a function h and use this precomposition with the unit. So, right, nice. What else do we need? And here, our final sort of point is assume our function h, assume x, and then we just apply h to f of x, which we already know we have, and x reflexivity. Okay, so this is an equivalence pretty straightforwardly by using property of propositional truncations. To prove that this is equivalence, this is straightforward. Don't need to use too much. To prove that this is an equivalence, here's where you need the surjectivity proposition part. I mean, here you also need in the bottom, you need here that is contradictive proposition in order to actually make sure that you are able to use the property of truncations. So in the end, this provides us with the fact that this precomposition is an equivalence. So instead of producing a proof of usual contractible fibers, now produce a term of, by this equivalence of for all A and A is contractible fiber of F at F of A. Okay, good. Everything clear? Can I quickly get a yes or no in the chat just to make sure nothing is buggy currently? Okay, nice. Right, so, okay. So, so need so fix a term A of A, generalized element. I first need something in the fiber, the actual inhabitants, times equals FA. So take just A and REFL at A. So, right, so now that we have passed this equivalence, we actually know what's its inhabited, what the fiber over F of at A is inhabited by. It's inhabited at A. And the proof of the fact that it's inhabited by that is just reflexivity. So everything works out fine. Okay. Now we need to show that it is the center of contraction. So take some dependent pair where our first element is an A. And again, our second element is from this equality. Okay. Now, we use the fact that F is an embedding. So we get their application at F, which goes from x equals A to f of x equals f of A is an equivalence. So in particular, it has an inverse. So we already have our P here, and this will be sent to app at F inverse P. Okay, just making sure that our equalities are nice. We also need to invert it. So so first we have the equality that A is equals to X, namely let's say P inverse APF inverse in A equals X. So by characterization of equality in sigma types, suffices to transport and then look at the second part of our equalities. Consider suffices to show so that when we transport by this PF minus 1 inverse of reflexivity, we actually get P. Okay. Now lemma is that by a lemma we can actually see that this type here REFL at f of A is actually equal to the application of F to this entire term. Taking its inverse and then composing, and the inverse here is taken basically only to make sure that we have what I want to say, that we can concatenate paths as well. And we concatenate with reflexivity. So how so? Well, use this general case. So instead, take some t from x equals A here. So these are just generalized elements we can assume. So we can actually perform induction. So we can perform induction on T to get transport at REFL of x at REFL of f of x, which is equal, of course, to reflexivity. But this is also, this is definitionally equal to reflexivity, right? So, which is also the case for AppF P, no, REFL -1 concatenated with REFL and f of x. So everything works out fine after you perform an induction. So again, you can generalize this to a lemma, and after so instantiate at applying this application function here. Okay, so hence we need a term of what? So by our identification, we only need a term of this equals P. And I want to say we concatenate here with REFL, f of A equals P. Yet concatenation with reflexivity doesn't do anything. Then as these are quasi-inverses, they cancel out. And moreover, inverting a path twice gives you the path itself. So let's say this means quasi-inverse property. This is double inverse of path. And this is reflexivity concatenation. Okay, so with this, we established an equality on the second component. And so this gets us the desired equality for every x and p. And so we are done. We indeed produced the proof of an equivalence. Okay, all good? Do you have any questions at this moment? I think the only troublesome part with this one may be just defining all of the necessary sort of type families for the lemma. Other than that, it should be quite easy. Okay. All right. Now we then, if there are no questions, go to probably the most interesting property that we will be talking about in this problem session. It's problem 4. This is Levier's fixed point theorem. So why is it so important that it actually has a name? This is a generalization of several diagonal, so-called, arguments such as Gödel's incompleteness theorem, Cantor's diagonalization argument for reals, as well as Russell's paradox. Basically, Levier's theorem tells you situations in which you can actually find fixed points on some nice functions in order to possibly introduce some pretty interesting consequences to your system. And so it's a really interesting property, and I urge you to read more about it and why it actually deserves to have a name behind it. So, okay. So Levier's fixed point theorem says formally there exists, if we have the mere existence of a function f, okay, mere existence of a function f so that it's rejected. Well, let me first introduce the fact that let A and B be types. And f, a function from A to, well, f is already introduced, okay. So let those be types, okay. So if we have the mere existence of a function f such that it is surjective in the in this function space here, then we should be able to get an element of for all h and b to b exists b to b. So there exists a fixed point. Okay. So this is the formal statement of the theorem, and again, I think it's a very interesting one to really consider. So proof. It's a very elegant one, and I urge you also to formalize it, because with these sort of tricky things, it's almost as if you didn't do anything. And it's good, I think, to formalize this sort of results to make sure you understand sort of step by step what was missing, what was important in defining certain things a certain way. Okay, just in case at this point, are there any questions? And right, as usual, please yes or no in the chat, just so I make sure that you guys can still hear me. Okay, nice. Thank you so much. Okay, so we need to construct a function only in one direction. So remember, when existential quantification is always interpreted as the truncated sigma type, the for all kind of directly corresponds to the pi type as soon as we are quantifying, as soon as we're taking a function space over a family, which is pointwise proposition. So let x in merely exists f to a to b. So in the fact that there exists a surjective function f. Note, codomain is a proposition. So we can instead, again, using the property of propositional truncation, instead assume also by using induction that we have double element f from A to B, and regarding what various I suggest. Yes, yes, yes. Conceptual Mathematics is a really good book. It's worth checking out. Okay, so in P, which is going to be populating the type that it's going to be a witness to the fact that F is surjective. Okay. So now fix. So this is, we can interpret this as a pi type, right? So we can fix an H from B to B. So define F from A to B as follows. By F at A is gonna be basically, so H is from B to B. So it's applying H, this endomorphism, to this sort of diagonal entry of F at A. So F is a function, again, that takes two elements of A. And so we apply it here to get to B, and then H to actually get back to B. Okay. So now what do we need? We need the fact that there merely exists a B, such that B is a fixed point. Okay, so recall is surjective at F F. Let me, yeah, F. So we have F at A is gonna be of type A to B, yeah? So applied it to one argument, the other one is done. So actually, that's not what we want to have. What we want to have is we've constructed this function f, right? And so we hence know that there merely exists an A and A prime and A, such that A prime applied to this is going to actually give you this f that we specified before, which is applying h to this fixed to the diagonal. Okay, so by propositional truncation, since what we want now is to get an element of this proposition here, we can assume we have an actual witness of the fiber, so A and A, and Q from f at A prime equals F. Okay. Claim H at F at A and A is our fixed point. Okay. In particular, H applied to F of the fixed point is going to be F at A. But this is true by definition. Okay. And applying our unit of truncation, you get the needed result. So everything works out fine. in particular, I'd rather put primes here everywhere. So we're actually getting our claim. So, okay. So as you have noticed, it's sort of, it is very elegant in the end. When you use definitional equality to prove equalities of functions, you almost never do that. Functions are almost never definitionally equal. However, here the amazing part is that these, as long as you define this function and then use the fact that the fiber is situated, at the very least you can assume it is, then you can actually get this fixed point to which you can apply it. So it's almost as if you define this f not to actually get a fixed point, but to instead get this element of A to which you can apply all the needle. I meant fiber inhabited. Okay. So this is probably the most elegant one that we're going to see. The final thing that we're going to do, we're already occupying quite a lot of time. So what I'll go over is problem 5a kind of quickly, just making sure I can sort of, maybe in case you were stumbling on it, sort of help you with formalizing certain parts of it, because the solution is certainly great, but it's a little bit informal. So maybe I wanted to introduce 1-2 additional types that might help you deal with this sort of question. So recall first, how do we define fin n? N is defined by induction. So fin at 0 is empty, and fin at n plus 1, just fin n plus 1. Okay. So, as usual, we have this identification, which you can read more about in Egbert's book. So we identify 0, for example, as in right of the unit in fin 1, and as in left in right of the unique element in the unit in fin 2, etc. And similarly with other natural numbers, so that we might use these notations nicely. Okay, so now claim is that the fin set of n to the power of m is going to be equivalent to the type of functions from m to n. Okay, so this is sort of very intuitive result that we want to be able to prove. So proceed by induction on m. Let m be 0. Then what do we have? Fin n to 0. This is going to be the same as fin 1, right? Just definitionally, which is going to be equivalent to, well, this is just mt plus 1. This is going to be equivalent to 1, right? And on the other side, we have fin 0 to fin n. Okay. This is going to be equivalent to, it's not just going to be equivalent, it's going to be definitionally the same as the empty type, the function type of the empty type going into finite type at n. which is, so the empty type is the initial object. It's pretty easy to see that there's only gonna be one, at least up to homotopy function in it. Okay, so we have this and this identifications, which allows us to sort of lift it up all the way. So we have the needed equivalence happening. So now for the inductive step, for m in k plus 1. So what do we want to show? That the finite type of n to the power k plus 1 is equivalent to finite type k plus 1 going to a type of n, given the hypothesis here. Okay, so the solution uses this informal way of saying, right, so we have the sum of n times going forth and the multiplication. You know, it's a little bit hard maybe to straightforwardly sort of situate it inside of a type theory. Define, if you want to formalize it, define n sum of a for n a natural number and n type by induction on n. So zero sum a going to be equal to the empty type, and what n plus 1 sum a is going to be a plus n sum a. So this exactly corresponds to coproduct of n copies of a. Okay, so similarly for products, for n prod a, I want to say. So what do we have first? We have that simply by the definition of the operation f to the finite type of n to the power of k plus 1. This is going to be just finite type of nk plus multiplied by n, which is going to be equivalent to n sum finite set of n to the power of k. So this is something that you can actually check. Proof at home by induction. You may need to prove certain supplementary lemmas. Yeah, what do I want to say? Right, and claim for any type A, and sum A is going to be equivalent to a product when type at n. So show by induction. Okay, so at the base case, we have n sum a and a times fin at 0. So this is by definition going to be the empty type. This is going to be by definition a times the empty type. These are going to be equivalent. So we can live this equivalence here. Okay. For the inductive step. So we have a plus n sum a equivalent to a times fin n plus 1, just by unfolding definitions, just to save time, is going to be equivalent to, by the inductive hypothesis, to, well, it's going to be equivalent just by simply distributing products as fin n plus a times 1 is going to be equivalent to n times fin n plus a, of course. And here we have, so this is what we want to show, I want to say, so we don't want to fill that in yet. So this is going to be just a coproduct of identity, which is an equivalence, and the induction hypothesis, which we had, is also an equivalence. So this is also an equivalence. So this establishes an equivalence here. So all is good. Okay. So by previous identification, the finite type of n to the power of k plus 1 is going to be equivalent to n to the power of k times fin n. So by induction hypothesis, right, we can exchange this type for a function type. By the induction hypothesis, suffices to construct a function this. So this is our induction hypothesis. This goes from our identification here times fin n, and we want to make an equivalence with the original function type, and k plus 1 to fin n. Okay. So in the forward direction, by induction, take g, which is our function from fin k to fin n. We take our y in fin n. No, we should say this. We should follow the alphabetical order, and we should take y in fin n plus 1. Okay. Nice. And we send it to g at y if y is less than k, and x otherwise. So note one thing that this sort of less than identifications, it works as we're again assuming that the elements of our finite types are going to be natural numbers, as if. So moreover, note for bounded cases, equality of natural numbers is decidable. So we can actually postulate functions this way. Type theoretically, there's a lot that you need to formalize and use, but generally, you have bounded quantification to consider on the natural numbers that makes your equality decidable, and that allows you to construct a lot of the functions of this form. So okay, So the last thing is to construct the inverse. Inverse is given by taking g of our function n plus 1 to type it in. And we send it just to g, which is going to be just simply what I want to say, restricted to the, this should be k. Don't know where this popped up. To the k first components, and then apply g to k. Okay. These are quasi inverses, which you can easily check, and we're done. Okay, so we're already quite over time. So as I mentioned, the last problems of the worksheet will not be looked over in this problem session. However, I urge you to look at the other video of the problem sessions this week in order to possibly see it in action. If there are any other questions, I can answer them on recording. If not, I can stop the recording and we can discuss them afterwards. Okay, I see no questions. So again, thank you for participating and watching, and I'm going to stop the recording now.